Morning. This is our last problem in my series on solving for energy problems. So this one we're going to be solving for unknowns. So we've just been kind of building up to this moment. This is how you should really solve your energy problems to be the most successful on your AP exam. So here's our scenario. A 50-gram rock is launched in the air using a slingshot that is stretched 5 centimeters. The rock reaches a height of 3.7 meters before falling back down to Earth. If friction is negligible, what is the spring constant for the slingshot? Okay, so let's go ahead and list off some forms of energy that we see, and then we'll make a LOL diagram and then roll with it. Okay. So forms of energy, I see a slingshot, so that means something is being stretched. So we definitely have spring potential energy, which is going to be in our initial snapshot. And then I also see that it's reaching a max height. So that means that we are going to have gravitational potential energy in our final snapshot. Since the slingshot is no longer going to be stretched, we're not going to have any spring potential energy in our second snapshot. It says friction is negligible, so we're not going to have any thermal energy. And since we're picking that point as our snapshot with the max height before it falls down, it's not going to be moving, so there is no kinetic energy in either snapshot. Let's go ahead and do the O part of our LOL diagram and then put in our X's for the stuff that we already know doesn't exist. So we know we have a slingshot. We know we have a rock. We know we have the Earth. That's it. That's all the objects in our system. We know that there is no kinetic energy in our initial snapshot. I'm going to go ahead and say also that there's going to be no height because we don't have any information numerically about height. So we're not going to deal with that. We're just going to say that the height for the slingshot is 0 in the initial snapshot. We are also going to say that it's not moving in the second snapshot, so no kinetic energy. We already said that there's not going to be any spring energy because the slingshot is no longer being stretched. And since friction is negligible, then we're going to have a thermal energy. That means that all of our energy has to be in spring and then to UG. So we can go ahead and make our bars since they're going to be identical anyway, and we can just add numbers on the bottom at the end. So I know it's going to be this much energy, however much it is, for spring, and then all of it is going to be gravitational potential energy. Okay, this is when this starts to be really powerful because based off of this, I can see that my energy forms before is just US and my energy forms afterward is just UG. So I'm going to be able to put together, I'm just going to write it underneath, to say that all of my energy before equals my energy after. My energy initial is just US. My energy after is just UG. Okay? And if it's just that, then I already have formulas, just so let's plug them in now. And that is going to be 1/2 kx squared. It's going to be equal to mgh, because the formula for, let's center this, so it's easier to read. The formula for spring energy is 1/2 kx squared. The formula for gravitational potential energy is mgh, right? So I'm just going to write that down right here so that I see it, I know it, all right? What is the unknown? What are we solving for? It's asking for the spring constant. So we're going to say the spring constant, which is the symbol K, right? Now we're going to show our work. This is why we wanted to have that equation before. All right, so I can go ahead and say, I'm just going to write it again. US is equal to UG, 1/2 kx squared, squared, is equal to mgh. I am solving for k. Before I plug in any numbers, and I do have numbers, before I plug in any numbers, I am going to solve for k first. Do the algebra stuff might cancel. Sometimes math cancels. It won't today, but sometimes it does make your life easier. Okay, so if I want to get k by itself, I need to get that 1/2 to the other side. So this is going to become kx squared is equal to 2 mgh, because I just multiplied by 2 on both sides. And then I want a lowercase k. And then I want to get that x squared to the other side, so I'm just going to divide it by x squared on both sides. So it's going to be equal, k equals 2 mgh divided by x squared. And that's it. Now I can plug in values. So I've got k equals 2 times my mass, which is 0.5 kilograms, times gravity, which is 9.8 meters per second, times my height, which is 3.7 meters, right here, 3.7 meters. And all of that is going to be divided by my x. Now, x, if you have forgotten, is how much your spring or your stretchy material is being stretched or compressed. So they're telling us that the slingshot is stretched by 5 centimeters. Remember, it has to be converted to meters. So we need to divide this by 0.05 meters. And we need to remember to square that value. Okay, so I'll just say squared. Okay, if I plug that into the calculator, I'm going to get a value of 725.2. And now you're wondering what the unit is. So I have kilograms multiplied by meters per second, multiplied by meters. So that's going to be kilograms times meters squared divided by seconds squared. But then I'm dividing it by meters squared, so those meters are going to be gone. So it's going to be left with kilograms per second squared, which is a really weird unit. So you can simplify it other ways, and it's going to become newtons per meter. All right, so how much force per meter you're stretching or compressing it with, okay? That's going to be the value for K, all right? That's pretty much how you solve your problem. So this is the process you're going to use. Hopefully this video has been helpful. If you have questions, let me know. All right. See you all in class.